more problems to help you understand how to calculate expected values. Let's start with this problem. One of the things you're going to know is what is the probability of hiring an additional teacher? And in this case, that's the probability that you have 71 or more students. That turns out to be 75% chance. With that, we can say, what's the expected value of hiring now? And in that case, it's simple. It's you pay $40,000. What's the expected value of waiting? Well, in that case, you pay 0 up front, but you will pay $50,000 if you need that additional teacher. And there's a 75% chance you need to do that. You do the math, and it works out to be 37.5, negative 37.5. So given these options, they should wait to hire because the expected value is less negative, right? There's a cost either way, but it's a lower cost by waiting in expectation. Notice, they'll never pay 37.5. They'll pay either 0 or 50. Expected value means if you did this exercise a lot of times, now on average, you would pay 37.5. Okay, let's do the next problem. Take a moment, think about what you think the answer is, and then watch the video. So we'll start with finding what the expected value for the policy for you. In this case, you pay $700, so it's a negative $700. But if you do need it, you'll get $400,000. And what's the probability you get that? Well, it's the 0.0002. You do the math, and you get negative 620. What's expected policy for company? It's exactly the opposite. They get $700, but if it's an earthquake, they have to pay the $400,000 out. And there's a 0.0002% chance that they do that. When you do the math on that, they get $620 in expectation. So if they sold 100,000 such policies and made $620 in expectation on each, that means that they would expect to make $62 million. Okay, here's the next problem. Take a moment and then we'll talk about it. In this case, there's two options. Fix the pipes now, or the other option is not fix the pipes. So, what's the expected value fixing the pipes now? Well, we know what it is. It's cost them negative 0.5 million, right? Negative $500,000. Now, if they choose not to fix the pipes, they pay 0 now, but if the pipes fail, they pay 10 million, and there's a 10% chance of that happening. Do the math, and that means in expectation it's a negative 1 million. Given this, they should choose to fix the pipes now because it has a lower expected value. This one is kind of based on the news this week. Obviously the data is made up, but it seems to be capture some of the rationale that is driving the recommendation from the American Academy of Pediatricians. Think through it, and then we'll talk about it. So there's these two options laid out in this problem. One option is in-person learning, and the other is distance learning. So in-person learning, there is a chance that you have a relatively negative bad outcome, a negative 80, but it's only a 1 in 20% chance, or 5% chance. When you do the math, that means it's a expectation negative 4 on these health units. Now, if you do distance learning, the cost is lower, but there's a higher probability of paying that cost, 60% chance. When you do the math on that, it ends up being negative 6. And so here, the risk neutral policymaker, if these are in fact the true data, they would be better off doing in-person learning if they were risk neutral. I don't know why I have risk averse there. I apologize. I will only ask you about risk neutral decision making. I'll just change that now because I can. Risk neutral. I won't ask you about the other ones on a problem set like this. Okay, let's talk about the building fairgrounds. So read through that and then we'll talk about it. So there are two options. So you can either not build, pretty simple, and there's an expected value if you build. Now if you don't build, it's just zero. You don't pay anything, you don't make anything. If you build, it costs you 10 million. But you may recoup that. There's a 20% chance you get 5 million. A 20% chance you get 10 million. And a 20% chance you get 20 million. When you do the math on all of that, you end up with negative 3 million. So in expectation, you would expect to lose money. And so a risk neutral policymaker should not build it. Again, to be clear, they might, if they might get lucky, they might be the 20% that makes 20 million. But in expectation, this is a bad decision, and a risk neutral policymaker shouldn't build. Okay, here's the last problem we'll go through. Look at it, and then we'll talk about it. So the city near the border has two options. They can order in January. If they do that, it's going to cost them 5,000. The other is wait until April. Now, if they wait until April, they don't pay anything now, but if they need things, they're going to pay 6,000. And there's a 90% chance they're going to have to pay that. So in expectation, that will cost them 5,400. So in this case, a risk neutral policy maker should order in January. Now, again, this is based on the probability of 90%. Let's say that probability had instead been 80%. Well, in that case, they would have been better off waiting. That's it. If you have questions, bring them to office hours and we'll talk through them.